Okay, good morning, everyone. Let's get started. So first of all, reminder, Friday is the due of the homework 3, which is all about the perceptron algorithm. It should be relatively much easier for the implementation and running, but again, don't try to rush like at last minute. Right? That's not a wise strategy. Right? Okay, so let us continue with the SVM. So in the last lecture, we talked about the training framework for SVM, right? So of course, first we talk about how do we formulate SVM objective function. Then by using the property that for linear classifier, you can actually skew the model parameters. It doesn't change the classification boundary, it doesn't change classification results, so that we do not need to explicitly compute the margin, because if explicitly computing the margin will require us to go over every training example, compute distance, then take the minimum one, right? So as long as we can restrict our model parameters in a subspace such that the minimum function margin is 1, so you don't need to do explicit margin computation. It's just 1 over norm of W. Based upon that, we actually formulated a constraint optimization problem, right? And doing some kind of simplification, and then we got a objective function of SVM in this form. And here, W is the augmented version, right? Remember the notation of sugar, where we fold the bias parameter B into W. So W0 is actually the original weight vector, right? And Xi is augmented 1 to account for the bias parameter B here, so that this functional margin is simply W transpose Xi, right? And this term is called the hinge loss, right? We talk about why it should be viewed as a loss. Essentially, it is kind of penalty, right? And on the different cases, what kind of penalty we incur based upon your current prediction, right? And then this term is called regularizer, right? And this regularizer in SVM context is to encourage you got your linear classifier to have a maximum margin, right? And the reason is the maximum margin you have, the smaller this dimension of your search space. That means your tighter your generation error bound. They're all well connected through the computational learning theory, right? Although this connection is a bit kind of like lengthy, and but we do want you guys to know how we finally arrive at this SVM objective function, right? And once we have identified the SVM objective function, we can develop a different optimization algorithm to optimize the model parameters W and B, right? According to the model parameters, we talk about gradient descent, which we know that for large data size, the gradient descent is pretty inefficient in that you have to go through all the training examples to calculate one gradient, perform one update, which is really, really slow. So in practice, when data is large, we always prefer stochastic gradient descent, right? So let us quickly go over this stochastic gradient descent framework, right? We suppose we are given a set of training examples, right? We initialize our weight vector to be 0. Of course, you can initialize them with other values. Here we just give some 0, right? And then we go over the training data set many epochs, right? Here, the maximum number of epochs is actually some kind of hyperparameter you need to choose according to your application, right? And inside each epoch, every time you're gonna random pick out one example xi, yi from the training set, then we're gonna repeat xi, yi, right? Suppose your data set contains big N examples, we're gonna repeat these examples for big N times to fake a data set of the same size of the original data set. Then we use this fake data set to compute the loss, right? The training loss, which still includes a regularization term and the hinge loss term, because hinge loss now is the same for every example, because those examples are just duplicated again and again, right? So you can just multiply the hinge loss over this random sampled xi, yi, by big N, right? And here, the constant C is some kind of hyperparameter to determine the trade-off, right, between the regularizer and the data-dependent loss, right? And then our goal is to compute the gradient of this guy, right? And we use the gradient of this guy. This gradient is viewed as the stochastic gradient, right? Then we use this gradient to perform the gradient to update over the current model parameters. And the step size gamma t is also referred to as learning rate. Right? And then we finish one update, and then we run and pick up another example. We'll do the same thing. We compute the stochastic gradient with which we update our model parameters. We'll do it again until we have sampled the same number of examples from the training set. Then we finish one epoch. Then we go to the next epoch. We do it again until we finish all the epochs. That's the stochastic gradient descent framework, right? So in the last lecture, we also explained why we should do this, right? Why this is a stochastic gradient, right? So again, we don't require everyone to know why this is called unbiased stochastic gradient, but we just leave the reference here. Like if you want to look at why we should, run and pick up one example and then duplicate and to fake the data set as the same size of the original data set, and plus the regularizer and the calculate gradient. So those derivation, several lines of derivations shows you actually following this procedure when you compute the gradient, this is actually an unbiased stochastic estimate of the exact gradient. In other words, if you take expectation of your stochastic gradient, you will recover the exact gradient. Right? And the stochastic optimization theory tells us that if you can guarantee that the stochastic gradient is unbiased, meaning that you take expectation, it is the exact gradient. Then with proper schedule of the learning rate or step size, they're gonna guarantee to converge to, roughly speaking, it's a local minimum, but more rigorous speaking, it should be called like attraction basin with probability 1. Okay, so before we talk about something new or any question, we just want to sync our thought and be sure everyone is on the same page. Mm-hmm. Mm-hmm. Yeah. You can random pick up an example without replacement or with replacement, or you can just random shuffle. It doesn't matter. Yeah. With or without replacement doesn't matter. Yeah. It does matter as long as you like the number of examples you sampled is the same as the data size. That's fine. Another question before we move on? Okay, great. So here I want to highlight the result that the algorithm is guaranteed to converge to the minimum of our objective function here if gamma t is small enough. Right? Later we'll introduce two sufficient conditions that how do you schedule gamma t to ensure this stochastic gradient descent framework converges, right? But before that, we want to give kind of like systematic or more general comparison of these two types of optimization approaches. One is called gradient descent, one is called stochastic gradient descent, right? So I want to visualize that to give a more intuitive sense about that. Okay, so suppose this is our contour lines of the objective functions. So while each contour line represents the function value, the function of the same value, right? So the middle here is actually a minimum, right? So suppose we're starting from here, right? So you can see the gradient descent. The trajectory of the gradient descent is like that, right? Every time I compute the exact gradient, which indicates where the function is going to decrease. Right? Of course, gradient indicates the increased direction of the function, but you take the opposite direction, actually move toward the direction that the function decreases, right? So you can see that as long as every time I guarantee I kind of like decrease the function value, it doesn't need many steps to arrive at the minimum, right? So again, it might just take like less than 10 steps or tens of steps, right? But what about the stochastic gradient? Okay. Okay. Stochastic gradient is like, although every on expectation, right, those stochastic gradient is the exact gradient. That means stochastic gradient itself is a random variable, right? You take expectation of this random variable, you recover the exact gradient. However, because each time you just random, right, just a random direction, so it doesn't necessarily align with the gradient direction. Okay? So when you run the stochastic gradient descent to minimize some kind of function, you like a, it's kind of like a random behaviors, right? It's like a drunk driver, right? Like you drive randomly toward north, then south and southeast and northwest, and go on. The amazing thing is that if you can guarantee your every time this drunk driver to drive a distance, right, which actually is the step size, right? If you can have some kind of guarantee about this driving distance, right, with probability 1, although you kind of like a random drive, looks like random drive, it will eventually still arrive at his house. That's the behavior of the stochastic gradient descent, right? So this messy trajectory, what's the advantage of this messy trajectory? Okay? So you can see that even you guarantee to finally arrive at your house, right, eventually, but you do need many more steps, right? Many direction changes and moving to arrive at the target place, right? But each move is quite cheap. Right? That's the major advantage. Right? If you look at if we contrast to the gradient descent behavior, right? So although I don't need too many steps, I don't need too many moves. I only need like for example 12 or 15 moves, but each move is extremely costly when the data is large, right? Because to compute one right direction, I have to go over every training example, right? And sums up the loss gradient together, I can get exact gradient, right? So even one update is really costly. So that's not favorable when the data is extremely large, right? On the other hand, although stochastic gradient descent, their updates kind of messy, kind of random, but each update is really cheap, right? I only look at one example or a few examples. I can do the update, right? And when the data set is very large, actually, the cost of this total number of messy updates can be far less than you go over the entire data set. That's why in the stochastic gradient descent framework, it works well in a large data scenario. Okay. Now, let us look at how do we instantiate the stochastic gradient descent framework for SVM. Right? So as we just mentioned, right, we have come out a stochastic objective function by random pick up example. That means every time I random pick up an example from the training set, and then I treat xi, yi as a full data set because I duplicate for big N times, and then I look at the objective function over this duplicated data set, right? Then I want to compute the gradient on this fake objective function, right? But here we found a problem, right? So this is a stochastic objective, right? You random pick up some example xi, yi, you duplicate for big N times to maintain the same size, right, as the original training set, right? Now the objective function over this thick data set will be regularizer plus the hinge loss on xiyi multiplied by n, right? Times this constant c, right? When we compute the gradient, we have met a problem. That is, this hinge loss is not differentiable, right? So this is actually a discrete function, max is 0 and something else, right? It's not a continuous function, and it's not differentiable, right? Then how can we carry out stochastic gradient descent framework, right? Stochastic gradient descent framework, at least you need to provide some gradient. Right? Then how do we sidestep this issue? How do we get over this issue, right? So we're going to introduce a surrogate of the stochastic gradient. The surrogate of the gradient is called subgradient. Okay? So what is subgradient? We can view it as a generalization of gradients to non-differentiable functions. Okay? So it was enlightened by the behavior of the convex functions. So this blue curve actually is a convex function, right? And when we mentioned about convex functions, we know that every tangent line of this convex function, right, at arbitrary point, right? For example, this red line, this tangent line actually is below the entire body of this convex function, right? Yeah, this is some property of the convex function, right? You can take any other point, like for example, if you take this point and you draw a tangent line, right? Forgive my bad drawing, right? You can still see that the entire line is below the function body. Okay? So, and we know that the slope of any tangent line is actually the gradient of this function, right? And we know that, okay, given this gradient, we can draw a tangent line, and this tangent line will be below the entire function body. So a natural extension will be, okay, if at some point, like here, it is not differentiable, that means I don't have some gradient of that function, right? However, if I can still draw some line across that point, right? For example, here, right? Such that this function is still below the entire body of this convex function, then I'm gonna use the gradient of that line as subgradient, which you can view as kind of like a substitute for the true gradient, because true gradient doesn't exist. Right? So that's the idea of the subgradient. So let us look at some concrete example. Right? Just give you some idea, right? Rough idea. So we can look at this function, right? This is a convex function, right? For sure. And at x2, this function is not continuous. That means it is not differentiable, right? At x1, this function is differentiable, right? So let us first look at x1, right? So at x1, f of x is differentiable. That means I can calculate the gradient. I use that gradient to draw a line which pass through this point, right? So we got a tangent line, right? And know that this tangent line is below the entire body of f of x, right? And naturally, the slope of this tangent line is the gradient of f of x, right? Does it make sense? Okay. So now let us move to x2. For x2, unfortunately, there is no gradient of f of x. That means it doesn't have like tangent line. Right? However, we can see that we can draw many lines which pass through this point and also stay below the entire body of f of x. Right? There are many choices. Like one choice will be this line, right? This line, this dashed line. The other choice will be this line, right? Both lines are staying below the entire body of f of x, right? And of course, there are numerous other lines in between, which can pass through the same point and also be below the entire f of x. So that means we can pick an arbitrary line, such a line, right, and use their slope as the subgradient or subderivative. You can use them as exchangeable terms. Does it make sense? Right? That's the definition of the subgradient. So interesting point is that, okay, subgradient can be many, right? You don't necessarily expect that there is one unique subgradient. Actually, there can be numerous subgradients. Okay. So yeah, let me emphasize again. At this point, x1 is differentiable. So you can draw a tangent line which passes through this point, and the slope is actually the gradient of f at x1, right? But at this point, the function is not differentiable, but you can draw many lines which pass through this point and also stay below the entire function body. So any line which satisfy these conditions are viewed as subgradient, like G2, G3, and also many other slopes in between. Right? Okay, any question regarding this definition of the subgradient? Okay, perfect. So now let us look at how to compute the subgradient for SVM objective function. Right? So when we look at this objective function, of course, it is a kind of random objective function because we randomly pick up one example xi, yi, we duplicate for n times, we compute the hinge loss, which is not differentiable, and plus this regularization term, right? So this is a general curve of the max function, right? Of course, it is not differentiable here, right? So if we want to compute the subgradient, we know that. Let me at here, right? We know that I can find any line, right, which pass through this point. Which pass through this point, right, and now stay below the entire max function. Then its slope is a subgradient, right? But here we're gonna choose a very simple idea. Like I can choose this one, or I can choose this one, right? In any cases, in both cases, like they stay below the max function, so their slope will be subgradient, right? So that means when we compute the subgradient, we can consider two cases. One is that, okay, if this max function is simply 0, that means it is here, right? I can just take the gradient of 0, which is simply 0, as my subgradient, right? Of course, you need to take the gradient of this part as well. You add them together, you get your subgradient, which is 0, W0, and on this part, the gradient is simply 0, right? So you get the result. Okay. On the other hand, if your max function is the right input, which is 1 minus the function margin, right? And then I just take the gradient of this guy, right? That will correspond to the slope of this line, right? And then plus the gradient of the first term, you get your subgradient as W00. Here is just the gradient of this term subtracted by C, and now this is just the gradient of the second input, right? Then that's it. Now let us try to substitute those subgradient into our stochastic gradient descent framework to get our stochastic subgradient descent training for SVM. Right? So this is the definition of or how we compute the subgradient, right? So we initialize our weight vector, right? Say from 0, right? Then we go through the training data set many times, right? Many epochs. And then for every training example, xi, yi, we want to update our weight vector according to the subgradient, right? And how do we get subgradient, right? Following what we have derived, here's our updating rule, right? First, if this guy is 0, which means that this guy is less than 0, right? This guy is less than 0, meaning that the function margin is bigger than 1, right? The bigger than 1 will be the second case, right? And then your subgradient will simply be W0 and bias parameter. For the bias parameter, the subgradient simply 0. You just update W0, right? On the other hand, if the function margin is less than or equal to 1, right? Then 1 minus the function margin will be bigger than 0, and then the max value will be this term 1 minus function margin, right? And then the subgradient will be like this, right? You just substitute into the update, you get how you get your update according to the subgradient, right? So gamma t here is called learning rate. As we mentioned before, right? You have to ensure your gamma t satisfies some conditions to make your stochastic subgradient to converge, right? And here, one important hint in practical implementation, as you just mentioned, right? In practice, people before each epoch will always prefer to randomly shuffle the examples. Although, I mean, in theory, there's no difference. But in practice, people always like, okay, before every epoch, we first shuffle the training set. Then we just look at those examples one by one, according to the shuffle order. Right? And then look at every example, and then according to whether your function margin is less than 1 or bigger than 1, you get different subgradient. You use different subgradient to update your model parameters. Okay, any question regarding this stochastic subgradient framework? This is actually the weight vector and bias parameter, right? Remember, we used the notation of sugar. We don't want to explicitly write out the bias parameter, so we fold the bias parameter into the weight vector. So W0 now represents the original feature weight vector. And W actually is the augmented version with B included. 0, that means the subgradient for B is simply 0. Yeah. Excuse me? Separating for B, yeah. Yeah, for B. Other questions? Yeah. That's practical implementation. Like people always do things like that, right? But someone asked, okay, what if I just random pick up one example, a random pick up example? That's nothing difference in theory. But practice, people might feel like doing this, like random shuffling, doing one by one, will be more convenient. Okay, then hopefully, because in our next homework, you're gonna follow this algorithm steps to implement your stochastic subgradient descent training for SVM. Right? So be sure to be clear about every algorithm steps. Okay, now let us look at the schedule of learning rate. Right? So I actually mentioned this quite a few times that to ensure your stochastic gradient descent or stochastic subgradient descent to converge, you have to have some proper schedule of the learning rate. Right? So what kind of proper schedule? If your step size is gamma t, right? which includes the series of gammas, right? Gamma 1, gamma 2, gamma 3, blah, 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 blah. Right? If they satisfy the following conditions, then the stochastic gradient or stochastic subgradient descent framework will converge in expectation. That means will converge with probability 1. Right? So let us look at what kind of conditions. Right? First, every step size gamma t must be positive. Right? This is of course reasonable. Right? And then we require that the sum of the squares of the step sizes from t to 1, from t is 1 to t to infinity is finite. Okay. So if you write it more, write it explicitly, so it basically says if you add up the square of the step size at each step, right? This sum must be bounded. Okay. And the third condition is that if you just sum over all the step sizes, not taking square, then this summation must diverge. Let me write, sorry. Let me write it out. Right? It's t from 1 to infinity is gamma t. If you just sum over gamma t's, right, it must be unbounded. So these are like two sufficient conditions. And if you got a chance, I mean, if you're interested in time, we'll look at some stochastic optimization book. They're gonna combine like series, like theories of series and also some kind of inequalities to show that if these two conditions are satisfied, then your model parameters like WB here will converge to some local minimum with probability 1. Right? It's actually, if you're familiar with those theory, I think it's in some kind of advanced calculus book or real analysis course. It's not easy to understand the proof. Right? But here, of course, we're not going to that point, right? So here, I just want to give you some intuition about this two. What does these two conditions? What do these two conditions mean? Right? So first one, if you sum over the square of these step sizes, this summation must be bounded. What does it mean? It means that, like, suppose this is your function, right? You want to arrive here, right? If you do stochastic gradient descent, this condition just require you that you're not gonna jump too wild. Okay? If you're jumping too wild, that could be the case that, okay, you're gonna jumping around forever and ever and never stop at the local minimum. That's basically what this condition says. But then what does the third condition mean, right? You just sum over all the gamma t altogether, then we require this summation must be unbounded, must be infinity. What does it mean? It means that, again, use this simple function as an example. It means that every step you must move enough distance. Right? Imagine that, okay, if my movement is too slow, like too small, right? Every time I just move a little bit, I might just stop at some places. I'll never be able to proceed. So this condition just says, okay, you must ensure every time you move enough long. Okay? And this condition says, okay, although you move enough long, but you cannot move too long. If it's too long, it will be the case that, okay, you just fluctuate. You just feel jump around and back and around, and never arrive at the right place. Does it make sense? Okay. That's the intuition. It's not dependent on the problem you're solving. That's the beauty of this theorem. Of course, there are some general requirement of the target function you want to solve, like it must be differentiable. Probably I kind of forgot the preconditions, but it's pretty general. Like perhaps it has to be Lipschitz continuous, but I forgot. I need to double check the book. But basically, it applies to a very wide family of objective functions. Yeah. And then what kind of schedule of gamma t will satisfy those conditions, right? So there are many. Now here we give two common examples, right? One is like you have some gamma 0. Of course, gamma 0 must be positive. It's some hyperparameter, and some a positive. And as long as you schedule gamma t following this, it will satisfy both conditions. Right? Another example is here. Right? So in our homework, we'll ask you to follow these two schedules to implement your stochastic subgradient descent for SVM. And you will see how the convergence train behaves. But in modern stochastic optimization techniques, like the one often used in machine learning literature, like especially neural network, like ADAM or Ada Grid or PROS, their scheduler is much more complicated than this. And they have some like momentum. They want to track the past status and aggregate those into the update. And they want to do the element-wise update of the model parameters. In most cases, you can just will them as some kind of black box library to optimize your objective function. Okay. So here are some like results. Is knowing results to show why in large data context we would prefer stochastic gradient descent, right? So suppose we want our optimization accuracy to be within epsilon. What does it mean? It just means, okay, I want my optimized model parameters, and this is optimized optimal parameters, and this is truly optimum. I want my optimized parameters, the distance between my optimized parameters and the true minimum, the distance is less than epsilon. Then a question is that how many iterations do we need to update to update our model parameters to reach epsilon distance within epsilon distance to the ground truth, right? So here are some results, right? For strongly convex functions, suppose you have n examples, you have d-dimensional optimization problem. That means you have a d-dimensional input. Then the number of iterations required for gradient descent to arrive at epsilon within epsilon distance to the ground truth is this, right? It's big O n times d times logarithm 1 over epsilon, right? And if you run stochastic gradient descent, then the number of iterations is upper bounded by some constant times d over epsilon. So what we can observe is that actually the number of iterations required by stochastic gradient descent actually has nothing to do with the data size, right? So now we can. Oh, first, is there any question regarding the understanding of this results? Okay. The meaning of this notations, everyone is clear, right? It just means, okay, how many iterations I need to perform to make sure that, okay, my optimized parameters is within epsilon away from the ground truth. Okay? And gradient descent needs this many of iterations, and stochastic gradient descent needs this many of iterations. So you can see that, of course, when you decrease epsilon, that means the smaller the epsilon you have, the logarithm 1 over epsilon grows much slower than 1 over epsilon. Right? That's where the advantage of gradient descent comes from. Right? If your n is quite small, right? See, we take some extreme example like n equals to 1. Then for the same epsilon, we can expect the number of iterations of gradient descent is much smaller than stochastic gradient descent because it's 1 over epsilon rather than logarithm 1 over epsilon. Right? However, if we consider the case that n is very, very large, that is the modern applications where you have a big data set, right? So your n can be 1 billion or 2 billion, right? And for the same epsilon, right? Even you take a logarithm or 1 over epsilon here, right? When you multiply a huge data size here, then the number of iterations for the gradient descent can still be far larger than the stochastic gradient descent, right? Because stochastic gradient descent, the iteration number has nothing to do with n. That's why in practice, when you have some big data, stochastic gradient descent is often more favored. Does it make sense? Okay. Is everyone comfortable? Right. Again, this is you're not required to show why this. This is kind of like classical theory. We just want to use some kind of algebraic results to showcase why we would like to prefer stochastic gradient descent, right? Especially when n is large. SGD is generally preferable when the data size is huge. Right? This can also be seen from their convergence analysis result. Okay. So we have finished the introduction of the how we train SVM, right? So last point I want to discuss that we want to compare with the last linear classifier learning algorithm, right, called perceptron. Right? Want to look at if there's some commonality between this stochastic subgradient descent for SVM and perceptron. Right? So first of all, if we look at this stochastic subgradient for SVM, right? This is a whole algorithm framework, right? For every epoch, we shuffle the training set. Then we just look at every example one by one, right? And then we follow this updating rule to update our model parameters. Now, if we compare with perceptron update, we found that the whole framework is surprisingly similar, right? The only difference is the updating rule, right? So for the SVM, okay, we got this condition, right? If this condition satisfies, that means function margin less than 1, I'm gonna update W for this, right? Otherwise, I'm not updating the weight vector only, right? With this guy, right? But for the perceptron, my updating rule is simply look at if yi times the function margin less than or equal to 0, right? Then I update this guy, right? So the only thing is that how we update W, right? And all the other steps are exactly the same. So now that this updating rule can be explained as using some stochastic subgradient to update model parameters, can we also explain this updating rule as another stochastic subgradient, right, for some other objective function? The answer is yes. Right? So if we write down the objective function of perceptron in this way, right, and to follow the same idea to compute the stochastic subgradient, right? So it's a max of 0 and minus y w transpose x, right? If we compute the subgradient, okay, when this guy, when this max value is 0, then subgradient is 0, right? And then that means the perceptron doesn't make any update, right? And when does this max function is 0? Yeah, this guy is bigger than 0, right? That means this guy will be less than 0, right? Right. Oh, sorry. Yeah. It's I make the wrong direction. So when is this max function is 0? That means this guy is the right input is less than 0, right? That basically means this product is bigger than 0, right? And this product bigger than 0 means that you make the correct prediction, right? So this actually is consistent with perceptron updating, right? When you make correct prediction, you do nothing, right? Because the subgradient is simply 0. Right? On the other hand, if the max value is the second input, right? So that means this guy is bigger than 0, right? That means this product is less than 0. And when this product is less than 0, that means, okay, you make wrong prediction over this current example, right? And then when I compute the subgradient, I just compute the gradient of this right input, which is simply minus yx, right? Now you apply the stochastic subgradient, you exactly recover the updating rule of the perceptron. Right? Any question? Okay. So now we have a very interesting conclusion that, okay, perceptron, well, you can view it as kind of at the first sight, we view it as kind of heuristic updating rule where, okay, when you don't make mistake, okay, you do nothing. When you make a mistake, you kind of like plus R learning rate times the product between the label and the input, right? But we can further explain it. This guy essentially is doing stochastic subgradient over a particular objective function. Right? This particular objective function is also having kind of form similar to hinge loss, but now only max 0 and minus y w transpose x. Right? There's no 1 here. Right? For the hinge loss, you got 1 minus y times function margin. Right? And for perceptron loss, you don't have constant 1 here. And the second difference is that, okay, we don't have the regularizer. Right? For the SVM, in addition to the hinge loss, our objective function also have a regularizer which penalize the models, right? We want to have the maximum margin, right? But for the perceptron, we don't have the regularizer at all. And based on that, we compute the subgradient, it aligns or is completely consistent with the perceptron updating rule, right? That's very interesting analogy. And from this, we can also see that because perceptron's objective function essentially doesn't have any regularizer, so it only cares about the performance on the training objective function, right? Which is actually not very good, right? Because the generalization error bound is determined not only on the training error, but also determined by some additional term, right? Determined by that term is determined by VC dimension, is determined by the number of training examples, and all the other steps, right? And perceptron doesn't account for that as well, at all. Right? Okay, so now I'll come to the summary, right? So from the optimization perspective, SVM essentially is to minimize the training of SVM, essentially minimizes regularized hinge loss. Okay? And we can use the stochastic subgradient descent to solve that problem. And we also found, surprisingly, that perceptual algorithm actually is also using the same framework, except that they choose a different loss. Right? But stochastic subgradient descent is not the only choice for SVM training. You can definitely use other optimization algorithms, like another commonly used one is called dual coordinate descent, implemented in this famous SVM library is called LibLinear. Right? Okay, so far, any question? It's here. Yeah, it's in a term. B is inside W here. So we'll compute subgradient, like say your max value is the right term, right? Your subgradient is simply the gradient of the right term. of course, you compute the gradient with respect to W, it contains the gradient of B. Yes, 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 yes. Other question? Okay, perfect. So now we need to talk about SVM dual. So far for support vector machines, right? We can talk about the training principle, right? Why should we maximize the margin, right? It can be justified while the computational learning theory, right? And then we formulate the SVM objective function, right? Which reflect the margin maximization principle, right? Then we talk about how to solve SVM optimization problem. Right? But so far we have never talked about why SVM is called SVM, right? What does support vector mean, right? So in the next or in the last piece of this topic, we're gonna address all those questions, right? We're gonna explain what do support vectors mean and what is the dual form of support vectors, right? And what's the advantage of using dual form to solve SVM optimization problem, and how can we leverage dual form to extend linear classifiers to nonlinear classifiers, right? And this trick is called kernel trick. It's a very common used trick in machine learning, right? So we're going to talk about first the dual form, the definition of support vectors. Then we'll talk about the general definition of kernels and the kernel trick. And then we'll talk about the properties of kernels. Then we're going to combine the dual form and kernel trick to extend our SVM to nonlinear classifiers. Right? This is our plan. Right? So this last piece of topics is a little bit mathematical. Right? Although at the end, like, you will see that your implementation of nonlinear SVM is extremely simple, 5 lines of code, right? But to arrive at that 5 lines of code, you need to know a series of reasoning chains, which is not hard, but it's kind of like lengthy. Okay, so I'll highly recommend everyone like going through after the lectures, right? Do need to go through the lecture slides and trying to catch up the logic flows. Okay, we're going to first talk about dual forms and support vectors. Right? So why do we want to talk about another optimization form, right? The motivation comes from our desire to deal with nonlinear cases, right? So although we're talking about linear classifiers, right, we know that it is of limited expressivity, right? In practice, the relationship between the input variables and the output of interest can be highly nonlinear, right? Then we can either like build up a nonlinear model from scratch, like a neural network we're gonna discuss after SVM, or can we work out some trick, right? We still maintain some kind of linear model structure, right, without modifying our linear model and training all those algorithms too much, but we can still be powerful enough to deal with nonlinear case, right? Actually, I have discussed the idea of this trick before, right? I also have done some practice of homework, right? So one idea is that we can explicitly introduce some nonlinearity into the feature space. So we can see that for this two-dimensional space, right? All the examples are represented by a point in a plane, right? Of course, this is not linearly separable, right? If you want to separate positive and negative examples, you have to draw some curve. But if we can come out some kind of smart feature transformation, right? For example, this is the transformation I come up, right? So my original instance is represented by x1 and x2. But now I transform them into a 4-dimensional input vector, x1, x2, x1 squared and x2 squared. Right? Now I can try to look at the positions of those points when they're re-represented or mapped into a 4-dimensional space. Right? And you see that actually they are in a 4-dimensional space, they are linearly separable. That's the key idea. Right? So if you can come out some like smart feature mapping or feature transformation, you map the original data points into some higher dimensional space. In that space, we can find out a hyperplane which can perfectly separate positive and negative examples. Then that's a win, right? If we can find out some space, right, then our task is just to, in this higher dimensional space, we identify the V vector and bias parameter. So that's the idea, right? That's the idea. This is how we're gonna expand our support vector machines to nonlinear classifiers as well. But later we're gonna talk about some more general trick, which is called kernel trick. Right? So first, before we do that, right, we need to know some dual form of SVM objective function. Right? So primal form and dual form are some kind of like basic terms in optimization theory. Again, we're not gonna go very deep to the optimization theorem. We just want to introduce some basic definitions, right? And so what is a primal form, right? We consider a general constraint optimization problem. Right? So we're not saying our objective function must be convex. It can be non-convex, doesn't matter. Right? So our objective function is f of x. Our goal is to minimize f of x subject to a set of constraints. Right? Those constraints are represented by m inequalities. Right? G1 of x is less than or equal to 0. G2 of x is less than or equal to 0 until G of mx less than or equal to 0. So basically, you can view like all the x that satisfy those inequalities form a subset of x, right? And those x is called the feasible region. Right? So we want to minimize f of x on this feasible region. Right? We want to pick up an optimal x in this feasible region, which minimize f of x. Okay. Does it make sense? Right. That's the general definition, right? Again, we don't make any assumption about the form of G1x, G2x to Gm of x, those constraint functions. They can be convex, they can be non-convex, doesn't matter. Right? Okay. Based on this general constraint optimization problem, we can construct an augmented function, which is called Lagrange function. Okay. I'm sure you guys have seen this form before, right? But now we're talking about it in a more general sense. So we can construct another function, which is not only function of x, but also a function of a set of lambda values. We call lambda as Lagrange multipliers. Right? So the form of the Lagrange function is f of x, the objective function, right? Plus a weighted summation of the constraint function. Right? Each constraint function, gi of x, is associated with a Lagrange multiplier lambda. So you can see that this body lambda actually consists of all those lambda i's. Okay. So again, we call this summation of the objective function f of x plus a weighted summation of the constraint function as the Lagrange function. Right? This function is not only a function of x, the original input, but also the function of Lagrange multipliers. So far, it's a definition. Everyone is good, right? Right. Okay. So now, a very, very good, very cool conclusion arrives, right? We can show that solving this optimization problem is equivalent to optimizing the Lagrange function with respect to both x and Lagrange multipliers lambda. Okay. But this optimization problem, the second optimization problem here, is a little bit non-trivial. It's a minimax problem. So the objective function is a Lagrange function, but in inner level, we're going to maximize the Lagrange function with respect to lambda. In the outer level, we're going to minimize the Lagrange function with respect to x. The interesting point is that in this optimization problem, we don't have any constraint over x. X is free. We put non-negative constraints over the Lagrange multipliers. And for simplicity, we're going to write this minimax optimization problem in this form. Right? We put the non-negative constraint over the Lagrange multipliers underneath the max. Right? So the claim is that we will solve this minimax optimization problem over the Lagrange function. The optimal solution will also be the optimal solution for this general constraint optimization problem. This is a well-known result in the optimization theory. Is everyone comfortable with the conclusion so far? Right? It just tell you some kind of result. Right? But someone asked why, right? Why these two optimization problem is equivalent, right? Actually, the proof is pretty simple, right? Although they look very different, right? The proof is pretty simple, right? So if we contrast this two problems, right? We want to look at why they are equivalent, right? So remember, the second problem is a minimax optimization. It's a bi-level optimization problem, right? So we can look at, right? You can imagine that, okay, in the outer level, I'm going to search over all possible x, right? Remember, in the second problem, in this problem, right, x is not constrained. It's not constrained by anything, right? You can freely choose x in the whole real space, right? So we want to look at, for different x, right, what does the inner maximization result give us, right? So let us choose some x, right? If x satisfy all the constraints in the first problem, remember in the first problem, okay, we define the feasible region of x, right? And inside this feasible region, all the points satisfy all these m inequalities, right? But in the second problem, suppose this is a whole x region, right? I don't restrict x, right? I can pick up any x, right? Outside of feasible region or inside the feasible region, right? So now let us consider the two cases. First case, if x happen to be inside this feasible region, that means x satisfy all these m inequalities, right? What does the inner maximization of the Lagrange function give? So first, we know that x satisfy all the constraints. That means g1x must be less than or equal to 0. g2x must be less than or equal to 0 until gm of x less than or equal to 0, right? And in the inner maximization problem, we want to maximize the Lagrange function, right, with respect to non-negative lambda, right? Then what's the best choice of lambda? Any thought? Yes, exactly, right? So you got f of x here, right? X here as x is fixed and f of x here, right? You add up a bunch of g functions, right? but each g function is less than 0, right? You want to maximize the whole function. Of course, I want to remove all possible negative terms, right? Then I should put all lambda I values to be 0 to reach the maximum, right? So if we choose all lambda I values to be 0, that means this term will be 0. Then your inner maximization will be f of x only, right? Right? And then that means your inner maximization will recover the objective function in the first problem, right? Does it make sense? Right? Okay. That's the result, right? So if your x satisfy all the constraints, that means it satisfy all the inequalities, then you have to set all lambda values to be 0 to maximize the Lagrange function. Then the Lagrange function will be the same as f of x, right? If, on the other hand, right, this is a feasible region, right? If you pick up any x value outside the feasible region, what will happen? We know that f x violates at least one constraint function, right? That means for some gi x, it must be positive, right? Because now you pick up x to be outside the feasible region. That means it must break some constraint, right? Then there must be some GIX which is bigger than 0 because it won't satisfy all the inequalities, right? Does it make sense? Right? And then in this case, if you want to maximize the Lagrange function with respect to non-negative lambda, what is the maximum value? Okay. We know that we add fx with some positive gix times lambda I, right? Now I want the whole function to be as large as possible. How should I choose lambda I? Yeah, I can choose it as large as possible, right? Because this guy is bigger than 0, right? I multiply it with lambda I, right? If I want my function to be as large as possible, I can pick lambda I to be as large as possible, say infinity, right? Then the whole Lagrange function, its maximum will be infinity. Right? Does it make sense? Right. So now we can aggregate these two cases, right? This is the second problem is by optimization problem, right? You can view like, okay, I'm gonna go through all possible x in the whole region, right? And for every possible choice x, I'm gonna look at the maximum Lagrange function inside, right? So know that for any x inside the feasible region, the inner maximization will give me f of x, okay? And for any x outside the feasible region, the inner maximization will simply give infinity, right? But overall, we want to pick up the x who gives the minimum value outside, right? And of course, all the x outside of this feasible region won't give you the minimum value because it's infinity, right? So the only minimum value possible should be x inside the feasible region, right? And then it gives us the result that, okay, this minimax essentially is to find out the best x inside this feasible region, right? And when x is inside this feasible region, the inner maximization always give f of x, right? That essentially search the best x in in a feasible region, which give the minimum f of x. Right? So now you see the link. Right? So now establish that, okay, actually you're doing minimax optimization, you're effectively just searching over x in a feasible region, which gives the minimum objective function f of x. That's the key idea. Right? Again, if you feel a little bit uncomfortable or feel like you missed something, don't worry. Right? Just look at the slides after the lecture. You will get it after like 5 minutes. Right? Okay, so now we have shown that any constraint optimization problem can be written as an equivalent minimax optimization problem over the Lagrange function. Okay? The benefit of this Lagrange optimization problem is that I get rid of all the constraints over x. Right? So in the original problem, like those constraint function can be very complicated. Right? So if you want to ensure that, okay, your x must satisfy all these m constraints, and then in this satisfied conditions, you want to minimize fx, is kind of like a non-trivial in many cases. Right? But if you can convert it to a minimax optimization problem, you don't need to worry about whether your x violates the constraints. Right? It's a free optimization problem. Right? You only need to add an additional non-negative constraint over lambda, right? But it's just bigger than or equal to 0. And this is it is much easier to deal with. Right? That's why in practice, when you have like very complicated constraint optimization problem, people often seek for a minimax optimization problem to solve them instead. So before we proceed, I want to mention that so far, what we have talked about is that we assume all these constraints are inequalities, right? It seems a little bit different from what we have learned during calculus 1, right? Where we only talk about the equality constraints. Right? Remember that when we do the calculus 1, we are solving some kind of problem with equality constraint. We construct the Lagrange function of the same form, right? And we just take the gradient of Lagrange function, we solve that, and then we address the problem, right? So now I want you to think about how to use the same framework to incorporate equality constraints. Actually, it is pretty straightforward, right? But it will be a good practice to help you understand those connections. You don't need to think about it right now. Right? That will be our homework. Okay. So now we define this equivalent minimax optimization problem as the primal form. So this is called primal form. Okay. And someone asked, right, does this order matter? Right? We first do maximization inside, right? Then do the minimization outside, right? What if we change the order of max min? But we don't change the objective function. We still want to optimize this Lagrange function, right? But now, in the inner level, what if we minimize with respect to x, and outer level maximize with respect to non-negative lambda? Will the solution be different? Any thought? Any guess? You guess they are different or not different? They're not different. Unfortunately, they are different. In most cases, they are different. Yeah. Okay, so we have primal form. That means we have dual form, right? So dual form is just a switch the maximum. So if you optimize the same Lagrange function, but in inner level, you minimize L with respect to X, then in the outer level, you maximize L with respect to non-negative lambda, then this is called dual form. And in general, the solution of the dual form is different from the primal form. And there's a knowing conclusion that if you got the solution for dual form and primal form, then the function value at the optimum, the dual optimum, will be upper bounded by the primal optimum. So at least the proof here, the proof is not hard at all, right? Several inequalities, but we won't go through the details. And again, we'll list the proof here as a reference for you. If you're interested, you have enough time, you just take a look. But here is the conclusion. That is, in general, the optimal function value of the dual will be less than or equal to the optimal function value of the prime. But there are some special cases. For SVM, the good thing is that the solution of the dual is the same as the solution of the primal. Okay. You see, it's quite a restricted family. Right? SVM, the design of SVM is really smart. It's a convex function. It's a FN constraints, so it can guarantee that you solve the dual form is equivalent to solving the primal form. Okay, let's stop here. We're gonna continue with the SVM dual on Thursday.